Welcome to the overview for the Agricultural Conservation Planning Framework. This presentation is an introduction to using ACPF for watershed planning. It was designed to introduce ACPF technology to people involved in conservation planning within agricultural watersheds. ACPF is a GIS tool that requires some technical expertise to be able to run the tools. However, this presentation was created to give people an introduction to the tool who don't necessarily have that GIS expertise. The goal of the ACPF Watershed Planning Training Series is to educate all stakeholders about the technology and how it can be used to facilitate conservation planning efforts locally. For ACPF to be used effectively, planners should have a basic understanding of the technology, its possible uses, and its limitations. This presentation will provide an introduction and overview of some of the key concepts watershed planners need to know about ACPF to start using the outputs for conservation planning. ACPF was designed to allow agricultural producers an opportunity to more effectively participate in local watershed planning efforts. For watershed scale conservation efforts to be successful, there is a need for multiple stakeholder groups to work together to achieve their common goals. ACPF was designed to facilitate this process by offering watershed planners a scientifically defensible and flexible method for citing possible options for conservation on the landscape. This photo depicts one way conservation planners use ACPF as a tool to facilitate stakeholder involvement. Here, conservation planners and technicians are using ACPF maps in the field with agricultural producers to identify possible solutions for site-specific resource concerns on the farm. So this presentation will cover what ACPF is and how it came to be, the three main components to ACPF, the ACPF outputs, and how to use ACPF as a part of the conservation planning process. ACPF was developed by the USDA ARS at the National Laboratory for Agriculture and the Environment. The ACPF development team at NLAE consisted of Mark Tomer, David James, Sarah Porter, and Jesse Van Horn. Most of these folks have now moved on or retired, so the current and future development of the tools and the data for ACPF is handled by the ACPF National Hub at Iowa State University in partnership with many state groups to support the expansion of the technology nationally. ACPF is a relatively new technology used for conservation planning in agricultural watersheds. It uses publicly available data layers to facilitate terrain analyses on small Huck 12 size watersheds. The tool was designed to allow agricultural producers and landowners a way to more effectively participate in local watershed planning efforts by offering them a menu of possible conservation options to choose from that could work on their farms. As mentioned on the previous slide, the ACPF has three main components, which are the theory behind ACPF, the standardized and consistent set of input data layers that's used to run the tool, and the last component is the ACPF toolbox itself, which consists of a set of tools used to identify that menu of possible conservation options to fit on the landscape. So we'll talk a little bit more about the different components of ACPF, starting with the theory behind ACPF. So the unifying concept for water quality management in agricultural watersheds is based on the conservation pyramid shown here. The ACPF is based on the watershed perspective of conservation. That is, what happens upstream affects what happens lower down in the watershed. The foundation of the conservation pyramid focuses on building soil health using in-field best management practices like reduced tillage and nutrient management. The ACPF tools do not focus on this part of the process because producers should already have access to information and programs to get started incorporating these practices on their farm through their local USDA service center. The ACPF tools focus on identifying additional opportunities for conservation as runoff leaves the field and travels through the watershed. These opportunities exist in a variety of locations throughout all agricultural watersheds. By stacking conservation practices along a flow path, we can build a kind of treatment train of multiple practices to maximize conservation efforts as runoff leaves the field and travels across the landscape. Utilizing areas on the edge of the field or in the riparian corridor may offer agricultural producers new opportunities to help meet water quality goals while avoiding removing land from production or altering their current farm management strategy. Four spatial data layers are required to run the ACPF toolbox. A feature of the ACPF is that these core data layers have been compiled and are ready to use for all of the Huck 12 watersheds shown in this map. This map is current as of September of 2022, so these watersheds are downloadable as file geodatabases via the ACPF download tool hosted on the ACPF website. The core data layers contained in the ACPF file geodatabase are a field boundary layer, a land use classification map, and a soils map. Additionally, users must supply a high-resolution digital elevation model that has been hydro-modified to model real-world surface runoff patterns. New watersheds continue to be added to the ACPF core database as the tool gains popularity and its use expands throughout the Midwest and Great Lakes regions. If a watershed of interest does not have a core data set available for download, the ACPF toolbox has a utility toolbox within it that can be used to build and structure the core data needed to complete an ACPF assessment. Now we will discuss each of the required input data layers in a little bit more detail. The first data layer is the field boundaries data layer. Field boundaries are derived from an old USDA Farm Service Agency database. The old field boundaries are edited to reflect crop-specific boundaries for each field in the watershed. Programmatic data is also removed from the layer to fully protect landowner privacy. Here you can see an example of what the ACPF field boundary dataset looks like. Each polygon in the layer represents a field with one of three classifications: non-agricultural, agricultural, or pasture grass alfalfa. This information is important for citing practices that can't cross field boundaries or that aren't appropriate where perennials are growing. The second data layer is the land use layer. The land use classification data comes from the USDA's National Agricultural Statistics Services cropland data layer, which categorizes land use into the dominant crop produced during each year. This data set is created annually for the continental US using a moderate resolution satellite imagery to classify the landscape based on extensive ground truthing. The ACPF uses that NASS cropland data layer to label each field based on the 6 most recent years of land cover. So it shows the dominant crop types within different areas of the watershed, as well as the crop rotations for individual fields. The next data layer is the soils layer. The ACPF soil data layer includes a selection of information from the USDA NRCS soil survey, including the hydrologic group of the soil unit, which indicates infiltration, and the percent of each unit classified as hydric. Hydric soils are those soils that are sufficiently wet in the upper part of the soil profile that will help develop anaerobic conditions during the growing season. The ACPF tool uses these soil unit attributes to help identify opportunities where specific conservation practices may fit on the landscape within a watershed. Finally, the last piece of input data required to run an ACPF analysis is the high-resolution elevation data, also called a digital elevation model, or DEM. The most common method used to collect this high-resolution elevation data involves scanning the surface of the Earth with an aerial LiDAR survey. These surveys are expensive to complete and produce a tremendous amount of data that requires a lot of technical capability to manage. Because of this, the availability of these data vary by location. Furthermore, where these data are available, there may be differences when or how the data products were collected or produced. For this reason, it is the responsibility of the ACPF technician to locate a suitable elevation product to be used within the ACPF. A DEM with a spatial resolution of around 2 meters per pixel is suggested for use within the ACPF tools. The raw DEMs often require several pre-processing steps in order to get the layer into an appropriate form to be used within the ACPF software. One of these important steps is the user hydro modification of the DEM. In this step, the ACPF technician makes edits to the DEM to ensure the modeled surface runoff accurately represents real-world conditions. This step must occur prior to running any of the ACPF practice siting tools and can be the most time-consuming part of the process. The hydro modification process is one of the most demanding and important parts of the ACPF analysis. Because elevation data is collected with a LiDAR survey from above the land surface, raw DEM products cannot see or sense locations where the surface runoff may flow underneath something like a bridge or through a drainage culvert. Because of this, ACPF technicians must locate areas within the watershed that produce this digital dam or false impediment to surface flow and manually edit the DEM data in those locations to allow for an accurate flow path to be modeled on the landscape. This is an important step because the DEM serves as the base for which the watershed delineation tools and all of the subsequent practice siting tools will be using. This process can impact how surface runoff flows across the landscape, where specific practices may be sited in the watershed, or even the overall nutrient load reduction strategy for the watershed. It is the responsibility of the ACPF technician to create a thorough and accurate representation of the surface water drainage network. In most cases, cuts and dams can be added to the DEMs based on recent high-resolution aerial imagery. But in some very flat landscapes, it may be necessary to incorporate field-based reconnaissance to validate the presence of catch basins or drainage culverts that may impact the flow of surface runoff. Each technician who completes a hydro modification of ACPF analyses may make different decisions. Therefore, other users of ACPF outputs should understand the potential sources of error and variability that exist in the modeling process, and these should be considered when using ACPF outputs for conservation planning efforts. All right, now that we've covered the first two components of the ACPF, which were the theory and the data layers, let's move on to the final component and talk about the ACPF toolbox, which is an ArcGIS toolbox. So the real superpower of ACPF is its ability to facilitate terrain analyses. Terrain analysis is the use of the high resolution elevation data to study the shape of the land and figure out how water flows and where it ponds, and how we can implement practices to alter water flow. This ability to do detailed terrain analysis is fairly recent and has been made possible by the ease of access to LiDAR elevation data. Access to this data source has had a profound impact on our ability to do conservation. Note that the ACPF does not do hydrologic modeling like SWOT or Sparrow. If anyone is familiar with those types of models, they actually account for precipitation and estimate how much water and pollutant loads will flow when or where. Whereas ACPF shows where water flows and concentrates, it is not used to estimate pollutant loads. The last component of the ACPF is the ACPF toolbox. This is an ArcGIS toolbox that was developed by the USDA ARS. The main ACPF toolbox consists of a series of toolboxes and tools within it aimed at guiding technicians through the necessary steps to complete an ACPF analysis. The individual tools are Python scripts written to semi-automate analyses of the landscape. The tools use standardized data layers as inputs, but offer the flexibility of adjusting specific parameters for individual tools so the outputs are best suited to local watershed attributes or specific program requirements. This is a list of the ACPF practice siting outputs available from the current version of the software, version 4. I won't go into detail about any of the specific outputs here, but you can see that there are a few different categories of the outputs shown. The ACPF toolbox allows users to choose which outputs or practices are best suited for a specific planning effort. And then by offering landowners this menu of possible options to consider to help meet local water quality goals, we are creating a new way for these individuals to start to engage in the planning process. The process of running an ACPF analysis also produces several intermediate layers throughout the processing chain that can be accessed as well if they are of interest to conservation planners. Some of the layers of interest could include the stream reach layer, which identifies perennial and ephemeral stream networks within the watershed. There's an area flow layer, which identifies surface runoff based on the contributing area and the topography. There's a slope layer, which is a DEM derived product. There's a stream power index, which shows areas of concentrated flow throughout the watershed and areas that are likely to form gullies. There's a topographic wetness index, which is a spatially continuous index of potential wetness that's based on topography and soil attributes. So these are just a few examples. There may be other layers of interest depending on the situation. The ACPF technician would have access to these layers. Here are a few examples of what some of the outputs from an ACPF analysis look like. On the left is an overview of the entire Hook 12 watershed, displaying a bunch of the potential outputs from this analysis. As you can see, there are many different potential opportunities to address nutrient sediment loss throughout the entire watershed based on this ACPF analysis. On the right, I've just included some screenshots of some kind of closer up images of what some of these specific practices look like, just to kind of give you an idea of what some of these GIS outputs look like on the landscape when you're actually zoomed into the field level. So there are different ways that ACPF outputs can be used. ACPF outputs highlight areas needing conservation practices and appropriate sites for common conservation practices. This information can be used by conservationists who study up before going to the field, helping them focus on the critical sites and realistic practices. Or the information can be shared with landowners to help them understand the needs and opportunities so they can share their judgment of the best strategies. So ACPF produces a menu of conservation practices for agricultural producers to choose from. The technology is intended to give landowners and other stakeholders more opportunities to engage in the watershed planning process. ACPF outputs can be used in a variety of ways depending on the specific situation. GIS technicians can create static maps at different scales, maps that highlight individual practices, or maps that highlight specific areas of interest. ACPF outputs can also be shared digitally or displayed using web-based applications, which can offer users a more interactive way to visualize the outputs and plan for conservation. That concludes the overview of the Agricultural Conservation Planning Framework. Thanks for listening, and for more information and learning resources, you can head over to the website acpf4watersheds.org.